Hello, this is Ms. DB, and in this lesson we're going to go over Chapter 11, Section 3 on sector area and arc length, and our objectives are to find the area of sectors and to find arc lengths. And both of these are just going to be part, like the area of a sector is just part of a circle, and the arc length is just part of the circumference of a circle. So there's really nothing new. You'll just be using what you have learned before and taking a part of it. Vocabulary is sector of a circle, segment of a circle, and arc length. Twice. All right, the area of a sector is a fraction of the circle containing the sector. To find the area of a sector whose central angle measures m degrees, you just multiply, you find the area of the whole circle and multiply that by m over 360. So if you have a circle here and you know what this measure is, like let's say it's 100, you would find the area of a circle by going pi r squared, and then you would multiply that by 100 over 360 if this measure was 100 degrees. So this is a sector. It's like a piece of pie. And you need to find the area of the circle by finding what fraction of the circle you have. Sorry, I accidentally grabbed something that started clicking on me. So think about a sector as a piece of pie. And then you're going to be finding the area of the whole pie times the size of the piece that you have, the fractional piece. Sectors are named by the word. You have to write sector and then by the three letters A, C, B. Now if you just write A, C, B, we don't know if you mean this angle. We don't know if you mean maybe well, it wouldn't be an arc, but we're not sure until you write the word sector by it. So it's important that you do that. And it's good to write the degree symbol after m to help you remember that this will be a degree measure, not an arc length. Okay, so we want to find sector HGJ. When they write sector, they are implying that we will be finding the area of the sector. It's understood to mean that this is the area we're looking for. So here's this shaded in kind of bluish gray area. And we know that that piece of pie is the size 131 over 360. If the whole pie is 360 degrees, we only have 131 out of that 360, and we need to multiply that by the area of the circle. But the area of the circle is pi r squared, so whatever that gives us times 131 divided by 360. So pi r squared, and then there's the fractional part. R is 12, so pi times 12 squared. Now on the calculator, you would take, if they want it in terms of pi, then multiply, 12 squared is 144, multiply that by 131, and then take that answer, hit equals on your calculator if you want, and then divide that by 360. If you hit equals, that will be the 52.4, and then you write pi after it. If you want to round it to the nearest hundredth, then you take the 52.4 and you multiply by your pi button on your calculator, and that will give you the 164.62. Okay, here's another example. We know that we have this kind of skinnier piece of pie here, so if we find the area of the whole circle, pi r squared, where r is 5, and multiply it by 25 over 360, that's really all you need to do. If you write it in terms of pi, then you'd have 25 times 25 divided by 360 is about 1.74 pi. And then if you multiply 1.74 times pi using your pi button on your calculator, you get about 5.45. So two different answers. This is just another example. This one's a little easier because you could do this one without any calculator at all. We've got 90 out of 360, which is 1/4 of a circle. And your radius is 1, so 1 squared is 1. So 1/4 pi, or 0.25 pi, is our answer in terms of pi, and then I would need a calculator to multiply that by pi, and that's about 0.79 meters squared once you multiply it. In this one, we'd have 36 over 360 times pi times 16 squared. It's really just more practice. All right, here's a little bit of a different problem. It says a windshield wiper blade is 18 inches long. To the nearest square inch, what is the area covered by the blade as it rotates through an angle of 122? So we've got 100, our central angle is 122 degrees, and we want to know, as this wiper blade, which is 18 inches long, moves along this way, it's wiping off all of this stuff. So it's this shaded sector here in that 122 degrees. So it's 122 over 360 times pi times 18 squared, and you will get 345 inches squared. This is almost the exact same thing, but it's a sprinkler, and it actually goes with page 765, so I'm not gonna, you can look in the book if you want to see how to do this one. Oh, this one's a half circle, so a half circle, you could just do this as 1/2 rather than 180 over 360. You can simplify your fractions if you know what they simplify to. Okay, here's another definition. Segment of a circle. It's a region bounded by an arc and its chord. A segment of a circle is just a little piece. We have an area of a sector, which is that piece of pie, right? And then if you draw the chord from here to here, all that you're left with, let me draw that in a different color. If you draw the chord connecting the endpoints of that sector, then you've got just this little piece of crust left over. That's called a segment. This little piece is the segment. The area of a segment is found by taking the area of the sector, this whole piece, minus the area of the triangle. Remember, the area of a triangle is equal to 1/2 base times height. And the area of the sector is m degrees over 360 times pi r squared. So the whole formula will be m over 360 times pi r squared minus 1/2 base times height. And we might have to do a little work to find some of these variables. So the 120 is the m. So we have 120 over 360 times pi times 9 squared. So this is all going to give us the area of the sector, 27 pi. Or you can multiply it together and find it. Now the area of the triangle, let's look at this. We know that we have 9 degrees here, or 9 centimeters here. This is also 9 because both radii are the same. And this is 120. If we need the height of this triangle, which is right here. Now because this is an isosceles triangle, I know that to find that height it's going to be cutting this angle in half. So this is 60 degrees and this would be 60 degrees. So here, let me draw what we have here. This triangle, kind of rearranged, is a right triangle. Here's the right angle. This is a 60-degree angle, and the hypotenuse is 9. Now we can't use Pythagorean theorem, but we can use trig. We are looking for the height right here. So do we want to use sine, cosine, or tangent? And because we know the hypotenuse, tangent is out. And if we did cosine of 60 degrees, the cosine of 60 degrees is equal to the adjacent over the hypotenuse. So you can take 9 times the cosine of 60 to get h. And then the formula of the triangle is 1/2 base, which we also don't know. We'll have to use that Pythagorean theorem after this to find the base, times the height, but then at least we'll have the height. We'll still have to find the base. So I'm going to turn the page so you can see this. So this was 60. These are the 9s. And you can use sine, cosine to find the measure of the height, or you can use the special right triangles. Remember the 30, 60, 90 triangles? So in a 30, 60, 90 triangle, a right triangle, if you know, which did we call this X or L or something? If you know X, then the hypotenuse was twice as big as that. And the third side was the short leg times the square root of 3. So this is even easier than using your calculator to find sine and cosine. In our problem, we know that this side is 9. So 2 times what equals 9? 4.5. And once you know the short leg, you can take 4. They said 9 square root of 3. Oh, that's the whole thing. Yeah, so this side would be 4.5 square root of 3. That's just from here to here. But the whole thing would be twice as big as that, so that would be 4.5 times 2 is 9 square root of 3. So the base is 9 square root of 3, and the height is 4.5. So we have 1/2 times 9 square root of 3 times 4.5, and we'll change that to, well, you could change it to it. I would. See, they're not done, though. They went to the next problem without finishing it. Oh, here's the rest of it. Okay, so we got 20.25 square root of 3. That's just a reminder of this special right triangles. All right, so now we can take our area of our segment that we found in step 1, which was 27 pi, minus 20.25. At this point, you would change everything to decimals, and you would get approximately 49.75 centimeters squared. So this was kind of a lot of work. Let's look at another one that isn't as much work. The reason it's not as much work, it's a 90-degree triangle. If it's a 90-degree triangle, it's going to be a lot simpler to find the area of this triangle. It's even simpler to find the area of the segment. The sector. So first of all, we need 90 over 360, but that's the same as 1/4. So let's just change this to 1/4. So we have pi times 16 times 1/4. 4 goes into 16 4 times. This all simplifies to 4 pi. So far we have 4 pi. That's the area of the sector. Let's see how easy it is to find the area of the triangle. That's not going to be hard either. The area of the triangle is 1/2 base times height. This is 4. This is 4. We can use Pythagorean theorem to find the base of this triangle because it's a right triangle. So we can say 4 squared plus 4 squared equals, or we don't even have to do that. We could call this the base and this the height. So we can say that this would be 1/2 times 4 times 4, so 16 divided by 2 is 8. So far we have 4 pi minus 8. That's the area of the triangle. And now it would just be time to get your calculator out and find what 4 pi is. It's approximately 12.56 minus 8. So you get about 4.56 meters squared for that little green piece. So it ends up being a lot simpler problem if there is a right angle in there. Okay, now we're ready to do arc length. Arc length is just this piece of the circle. The outer, like if you have a string wrapping around here, the arc length is just how long is that piece. So obviously the bigger the radius is, the bigger your arc length will be. So remember circumference of a circle is 2 times pi times radius. If you know the circumference, you would just multiply that by the fractional part of your circle that you have. So again, m over 360. All right, so here we have a circle with 8 centimeters for the radius. So 2 pi r is the circumference, and we need to multiply that by, what arc length are they looking for here? Oh, FG. FG is at a 134 degree angle, so we would multiply this by 134 over 360. Now you can multiply everything on the top, 2 times pi times 8 times 134, and then hit equals and then divide by 360. and we end up with approximately 18.71 centimeters. Look at your directions. If it says in terms of pi and rounded, then put them both. If it says or, then you can choose which one you want. So read the directions and see what they're asking you to find, what I'm asking you to find. Okay, they don't even draw a picture for this one, but that's all right. We need an arc with a measure of 62 degrees in a circle with a radius of 2. If you want a picture, radius is 2, and the measure is 62. And they want to know how long is it from here to here. If you were traveling across that apple and you were an ant, how far would you have to go? So 62 over 360 times 2 pi times 2. Simplify and you get in terms of pi and as a decimal. So arc length really is not that hard. You just need to find the fractional part of the circle, the outer part of the circle. So 40 out of 360 is the same as 1/9. You could simplify your fraction if you wanted. Should we do that? Then we don't even need a calculator. So this simplifies to 1/9. And let's see, 3 goes into 6 2 times, and in here 3 times. So I would end up with 4/3 pi, or approximately 4.19 meters. And that's it. The only ones that really might cause you a little bit of trouble is finding that little piece that is called a sector, the area of the sector, which you remember you have to take the area of the segment. No, I mean finding the area of the segment. Take the area of the sector minus the area of the triangle. All right, thanks a lot and have a great day.